Hello, students. Sitting outside on my back porch. Wanted to go over Chapter 9, Hydrologic Hazards at the surface, at the Earth's surface. Just give you some summaries regarding that chapter from the author's perspective. We're talking at first in this chapter, river systems. As you see in the previous chapter, um, chapter 8, rivers are important sources of fresh water. Waiting for the airplane. That was a helicopter, not an airplane. Rivers are an important source of fresh water. In addition, they are lifelines for transportation. They are a powerful geological agent of erosion and, as such, shape the land, surface, and redistribute earth materials. Large concentrations of human beings live in close proximity to rivers and are subject to flood hazards. Some of the basics about river systems are as follows. First, drainage patterns. Homogeneous substrate, river channels will form a tree-like, which is like what we call dendritic pattern, wherein the branches are tributaries and the roots can be likened to distributaries in deltas. Less tree-like patterns form as a result of topographic constraints and structural or stratigraphic fabric. Second, drainage basins. The catchment area of a river system in the sense that all runoff within this area contributes to the river and its tributaries. The boundary between drainage basins is the drainage divide. A good example for discussion, if we were in class, is the Mississippi River drainage basin. And then third, discharge. We're talking about the volume rate of flow of a river or stream that is equal to the cross-sectional area of a stream channel multiplied times the water velocity. Little math. This can be illustrated by applying this equation to a hose. Stream channel cross-section is roughly a half circle. Fourth, erosion. The erosive power of a river is a function of its energy. The steeper the gradient, the higher the water velocity and the greater the erosive power. Also important is channel shape, which is a way it redirects the erosive energy of a stream. To be complete, all other things equal, a stream with clear water has more erosive capability than one laden with sediment. This principle is important to the discussion of dams. Fifth, base level. The lowest elevation to which a stream can erode its channel. The ultimate base level is sea level, and lakes and reservoirs are temporary base levels. An important theme here is how rivers lose velocity when they reach base level, and how that affects the sediment load. Finally, sixth, graded stream. A state of balance within a river system, wherein a graphical profile depicting change in elevation with distance will have a smooth, concave upward shape. Generally, stream profiles get steeper in the upstream direction. Temporary base level changes disrupt this, and time is required for the stream to readjust to the new conditions. That's rivers. Now let's talk about stream features. Features resulting from erosional and depositional processes include the following. Alluvium, that includes sediment deposited by rivers and streams. 2, alluvial fan, a feature of arid areas formed by the intermittent flow of water from mountains toward a basin, resulting in an accumulation of sediment along the mountain front. These deposits have radially disposed distributaries, much like deltas. And 3, delta. We're talking about deposits of sediment in standing water, commonly at the mouth of a river. These deposits result from the rapid deceleration of river water as it reaches base level. Deltas commonly have multiple channels called distributaries that spread out from the main stream. Number 4, floodplain. We're talking about a broad, flat, depositional surface over which a meandering river flows. This surface broadens through time as channel shifting brings the river into contact with adjacent hills. Number 5, meanders. S-shaped winding stream channels that shift position continually by eroding the outside of bends and depositing point bars of sediment on the inside of bends. They are a feature of mature river systems where there is a well-developed floodplain. 6, natural levees. These are ridges of sediment that parallel a river channel. They are produced by natural flooding processes as water overflows onto the floodplain during high water periods. Commonly, these are adapted by man to be flood barriers. Finally, number 7, cutoffs and oxbow lakes. These are meandering river channels. They can at times intercept each other, producing a cutoff. This leaves a channel sediment stagnant. Oxbow lakes originate in this way. An oxbow lake close to San Antonio is Lake McQueen. An oxbow wannabe lake is off of FM 306 Fort Canyon Lake. Go 35 north to FM 306 west, or west on 306 to Canyon City. You can go tubing in this area. It's formed a horseshoe, 2-hour floating, tubing on the Guadalupe River. That horseshoe is the beginning of an oxbow lake. Let's talk about flooding and flooding frequency. It's an important theme that flooding is a natural process, especially in floodplains. Flood-related topics include, number 1, hydrographs, graphical representation of the variation of water level or volume of flow, discharge over some interval of time. Number 2, recurrence of intervals refers to the length of time between floods of a given magnitude. They're based on historical data compiled for a given stream. The longer the time interval addressed by the data, the better the predictive quality. The equation T equals parentheses n plus 1 parentheses divided by m is used. You'll see it in the book, wherein T is time in years. The n is the number of years in the record, and m is the assigned magnitude compared to other floods listed for a given river. Then thirdly, flood probability refers to the chance that a flood of a given magnitude will occur within a particular year. Where T, time in years, is the recurrence interval, and the probability is its inverse, or 1 over T. What about mitigation? The authors talk about mitigation. This falls under the heading of either physical structures or public policy. First of all, examples of large engineering projects designed for flood control include dams, flood walls, and artificial levees. Secondly, examples of smaller engineering projects including elevating houses and artificial flood. Third, final, public policy includes flood insurance, such as the National Flood Insurance Act of 1968 and buyouts of property owners in flood-prone areas. The NOVA program, flood, addresses this issue in the context of the aftermath of the Mississippi River floods in 1992. Then there's a little bit about urban development. Urbanization increases runoff by paving and roofing over natural surfaces. The net result of this is greater peak discharge and total cutoff, total runoff. Flood peaks also arrive more quickly than normal. There's case studies, one of when ice melts and moves, and one about the Nile River, 3 cubits between security and disaster. There's one in the Wayland, flood happened. One on a very wet fall in 1927. And then there's the last case study is the impermeable flood. It's all about urbanization, streets, etc. And that concludes my summary